most of the stuff that you'll see on the, doesn't it say if it's recording, it gives me a little noise?
Yeah, might be the top. Yeah.
It's recording.
Is it?
Yeah, you can see it.
Oh, there it is. Okay. Okay, so here we go. Okay, so we're going to go here, like I said. Kyle, can you see that?
I can.
You can? Okay, good. Okay, so we've already done some of this. So let me kind of go through the main things. Okay, we've already done this right here. Suppose this chapter is on thermodynamics. And like I said, if you know somebody that is studying science, studying especially chemistry or physics, they may have taken an entire semester class in what we're going over. And kind of the key thing in this chapter is this right here. If a reaction, just quick review, if it's spontaneous, and spontaneous just means it's going to happen, or non-spontaneous, which means it's not going to happen, okay? And so what they use, what they being AP is going to use, the College Board, 2 weeks from tomorrow when you take the test, they're not going to say spontaneous. They're going to say thermodynamically favorable. Okay, so you want to make sure you're ready for that when you take the AP test. And this, they would say not thermodynamically favorable. And that's kind of the main thing, the main overall things. And there are other things to this chapter, but is a reaction spontaneous, thermodynamically favorable, or not spontaneous, not thermodynamically favorable? And if a reaction is thermodynamically favored, it goes from the left to the right, just like it has for a year and almost 2 years now of chemistry. That's the way it goes. And either today or Monday, I'm going to relate this thing delta G, which I'm going to talk about this morning, to the equilibrium constant K and how they're connected. But if a reaction is non-spontaneous or not thermodynamically favorable, it goes this way. Now, how, with data that's given, and then I went through these reactions, which were all spontaneous, and I said, what determines whether reaction will be spontaneous or not? And it's, again, what we're talking about here is we're not talking about how fast does a reaction go. And we're not talking, does this reaction go to the right or the left? We're just simply saying, does this reaction proceed forward? Does it proceed to the right or does it not? Does this reaction happen or not happen? The criteria it's based on, ultimately it's based on this thing I'm going to talk about this morning called delta G. And delta G is called Gibbs free energy. And if delta G is negative, it's spontaneous. It's going to go to the right. And if delta G is positive, it is going to be non-spontaneous. And I'll show you how this works. And it's based on 3 factors. 1 is temperature. 2 is delta H. And typically when delta H is negative, when it's an exothermic reaction, it is more likely to be in this category. But not every time. Not every time. And the third thing is what I talked about at the end of class, which was delta S, which is entropy. And entropy is a measure of disorder. And I always think of my backpack or my dresser drawers or the inside of my car. The entropy, the disorder always increases unless I go organize things, unless I organize things somehow. And so systems tend to move towards a state if a reaction is exothermic to less energy and more disorder. But again, it is possible, and I'll show you this morning, for a reaction to have a delta S that's negative and still be spontaneous. So these are the criteria that's going to determine delta G, which is going to determine this. So same thing here. So temperature, so it's more likely for delta H when it's positive to be in this category, but not always. And then delta S, and I want to talk more about that, and when entropy or disorder decreases, it's more likely to be not favorable. Okay, so that's kind of a quick review. And I think we went through this. And I think we went through this page. Am I right? I think we did. Anyways, I'm pretty sure we did. Now into entropy. Okay, so now I'm going into some new stuff. So entropy, notice the units on entropy. Okay, remember the units on delta H, those were joules or kilojoules per volt. And that'll be important because we're going to get into some problems with numbers here. And this is almost the same thing. It's joules, but it includes temperature over Kelvin. Okay, so the units on entropy are a little bit different in disorder. And I'm going to show you here kind of what entropy depends on. So the rules for entropy. I don't know why they use S for entropy, but they do. I guess E was for energy or something, so probably some Latin thing there that I don't know about. So how you decide on entropy, and we're going to get into where we're going to actually get into some numerical problems with entropy today. But first of all, just looking at a reaction, just deciding what happens to entropy. So first rule is what it says right up here. So rules for, hey, Mr. Conyers, for comparing the entropy of substances is the state. And this is actually the way in a normal year that in a regular chem, I teach them, but the solid state has the least entropy. It has the most order, followed by liquid, followed by aqueous, followed by gas. And if you think about it, we're talking about disorder, unorganized. Well, a gas is the most unorganized. The molecules are moving very fast and they're spreading out. So again, we'll actually do problems here this morning where we're going to look at a problem and I'll say, okay, let's make a prediction before we do the calculation, and then we'll do and then we'll go through and we'll do the calculation. And we'll say, okay, does that make sense? Okay, then number two, and again, we're talking about unorganized disorder versus order. Number two, a substance that is hot has more entropy than the same substance that is cold. Again, if you think about it, if something's hot, that means the molecules are moving faster and they're going to spread out more. There's going to be more disorder. So number two here would be the temperature. So hotter means that entropy goes up. So the first thing is the state. The second thing is the temperature. Okay, and again, I know I'm probably going too fast, but I really am trying to hit on just kind of the main things. So I'm going to move on. Am I going too fast? Okay, number three is solutions. And I've kind of already said this. So solutions, aqueous, have more entropy than their undissolved solute and solvent. So this kind of summarizes that. So when you make a solution, the entropy is greater than the solid and the liquid that you mix them. And again, if you think about that, that kind of makes sense. The molecules are spreading out, they are diffusing. Okay, then here's the next one. So given that all the other conditions are the same, temperature, concentration, pressure, molecules with a higher molar mass have more disorder. So again, here's the flow chart. If we go through this and this, we come down here, the larger molecules have more disorder, have more entropy. And again, if you think about it, that makes sense. If we're talking about everything else is equal, the larger molecule has more subatomic particles, more protons, more neutrons, more electrons. There's more of a chance for disorder. And we're going to look at a table here. We'll look at some of these. But if I compare helium to neon, neon's on the shirt I just showed you. Well, neon is element 10 and helium is element 2. So helium would have less entropy because it's smaller, and neon would have more entropy because it's larger. Okay, so moving on. I'm trying to summarize things. More moles of a gas has more entropy than less moles of gas. That kind of goes back to here. So the more gas you have, the more entropy, the more disorder we have. That makes sense. And the more volume a gas has, the more entropy. So if I went here, more volume, more entropy. And to me, again, that makes sense, because if we have more volume, we have more space, more room for molecules to spread out, and there to be more disorder. Okay, so here, just as a table, just a couple points off what I was just talking about. So these are a table of entropies. And again, note the units here. The units are joules over Kelvin mole, like I just talked about a few minutes ago. But look at the entropy. Here are the gases, their value. Here are liquids, which are less. As I said, gases have the most entropy. And here are solids with even less. So that shows this right here. Okay, then compare two molecules that consist of the same elements, like here, NO2 and N2O4. And I said the larger molecules have more entropy. Well, if you look here, N2O4 versus NO2, well, this is larger. It has a larger entropy. Look at CO and CO2. Okay, so compare those two. Again, the larger molecule has more entropy. So this kind of just makes the point of what we were talking about. Okay, so the way to find entropy, and I don't think this, or just by inspection, and there's going to be a couple things on our formula sheet here. And if it's on our formula sheet, it's going to be on our test. At least I think it's going to be on our test. But entropy, and this is not, though. This is not. So the way you find entropy is equal to the entropy final minus the entropy initial. It's a little bit like delta H, okay? Or you could say the entropy of the products minus the entropy of the reactants. So it's the ending minus the beginning. So if we look at these scenarios, so the first one is freezing liquid bromide. So we end up as a solid and we started as a liquid. And so in this case, simply the sign, is it positive or negative? If delta S is positive, then the entropy is increasing, which is more pushing a reaction more towards being spontaneous. This would be negative. This one would be negative. Because we end up as a solid. We started as a liquid. The liquid would have more entropy. Okay, evaporate a beaker of liquid ethanol. Okay, simply, is it positive or negative? Is it positive or negative? And so what it's ending up as here, the product or the final is gas, and where it started out was aqueous. So this one, B, would be positive, meaning the entropy is increasing. Dissolve sucrose in water. Again, all we're asking here is entropy increasing or decreasing? Is entropy positive or negative here? What do you think? It's positive, right? Because it's ending up as aqueous, dissolved, and it started out with solid, sugar, and liquid. So it's positive. So this is increasing the entropy. So C would be positive. Cool nitrogen gas from 80 degrees to 20 degrees. So it's ending up as 20. It started as 80. What's going on with entropy here? It's going down. I agree, Jackson. It's going down. So D would be a decrease in entropy. And again, positive entropies are more likely to be spontaneous. Okay, so look at this reaction. This is what I'm talking about here. Again, we're going to do some calculations here in a few minutes. But on the product side, we've got a gas and a solid. And on this side, we have just a solid. So this would be positive because we're ending up, final or the product side has a gas, and the reactant side has just a solid. So E would be positive. How about F? Everything's a gas here, right? But here, this has two gas molecules on the right, and this has 2 + 1, 3. What's going on with entropy here? It's going down, right? It's negative. Whoops, I want to do that. Okay, A and B. Look at those, see what you think. Which has higher entropy? Which has more disorder? The larger the molecule, the more entropy it has. So for A, C2H6, C4H10, which has higher entropy, it would be the C4H10 because it's larger, bigger molecule, more entropy. And for B, same explanation, it would be this, the CH32NH, again, because it's bigger than this. So the higher entropy would be those two. And again, I know we're sailing here. We're going way faster than we should. Okay, again, I'm going to skip the next page. Let me just put it up real fast. There's nothing to write down here. It's actually almost more of a physics thing than it is a chemistry thing. But let me just go over this just kind of for your information so you can sound smart when you talk to somebody. You guys always talk smart when you talk to somebody. Me, on the other hand, I got to practice trying to talk smart. This is the first law of thermodynamics. And again, this is more of a physics thing than a chemistry thing. This I can't imagine would be on the AP test. It's not on our quiz, but it says the total energy contained in the universe is constant. Energy can change from one form to another. I have in my notes restated the first law of thermodynamics is impossible to get ahead with energy. The best you can do is get even. The best you can do is even. So the total, there's two main laws in all of physical science, which is chemistry and physics. And one of them is the law of conservation of mass. The total mass within the whole universe is constant. And then the law of conservation of energy, the total energy. The problem is that energy is converted into heat. Like even when we like this morning, I had my oatmeal and my bacon and a part of a banana, and that chemical energy is converted into kinetic energy but it's also converted into heat. And then I got in my car and I drove up to school, and the chemical energy in the gasoline was converted into mechanical energy, but was also converted into heat, which is not a useful form of energy. And then the second law of thermodynamics says any spontaneous process will increase the entropy of the universe, where entropy is a form of energy that is unusable. And so what the second law of thermodynamics says, it's impossible to even break even, is that perpetual motion machine is impossible. So anyways, just kind of a sidelight thing. Okay, I'm going to go skip this stuff. Okay, so I'm going to go on to the next page. Here is, okay, so this is on the formula sheet. So, and we're going to actually do a problem like this. It's on our quiz. This is something that's possible for the AP test. So I'm going to erase this here. And this equation, and all the way through the year, guys, I've even, and if you even care to look at this, I have got on my formula sheet, I have got written down a bunch of the notes that I've been telling you guys to. And if you guys care to write this down, all the stuff I've got in here, I'll be more than happy to let you take a picture of mine. But obviously on May 7th, 2 weeks from tomorrow, you're not going to get the handwritten notes. But to me, if you have it and you work on it on the mock test and everything, it might be beneficial. I don't know. You guys can decide. You guys, again, are, you know what's best for you. But this equation right here, if you look on the formula sheet on the back, where it says thermodynamics and electrochemistry, it is the second one. There's QMCAT, which is QSMAT, and there's this, which is exactly, if you look right underneath it, which we'll look at later today, we'll review the delta H, which we did in chapter 6 back in the fall, and we'll do delta G. So this equation is an equation that that we will, I think it's definitely on our quiz. It's definitely going to be on the Princeton Review, and it's going to be on the mock test or on the AP test. I would think somewhere. Okay, so to do a problem like this, it says calculate the change in entropy. You would have to be given this. So here's the S0, and the units on this are joules over Kelvin mole. So you would have to be given this. So CO2 is 214. CaO is 40. And CaCO3 is 93. And we're going to do this exactly like what we did way back in the fall with delta H. But first of all, before we do this, we're going to go back to what we were doing before. So the key thing here is this equation right here. And we're going to do this just like what we did. And this is why I want to go over this, because these are points. I think I said this, or I'm not sure I have, but to get a 5 on the AP test, if you get in the higher 70s or up, you get a 5. Think about that. If you get like high 50s, around 60 to like mid to 75 to 77, you get a 4. And if you get like 45, 46 to like 58, you get a 3. You pass. So every problem we can get right is good. Okay, it's like it's like every free throw. I'm a basketball coach. Every free throw you make helps our chances. So this is the kind of problem we can easily do. But first of all, if I make a prediction before I start, will this be positive or negative, what we were just doing? If I look over here, I've got a gas and a solid, and here's the solid. I think this is going to be positive. I think the entropy is going to be positive. So this is how I'm going to do it. So I'm going to use this delta S, just like it says right here, is equal to the sum of the delta S0 of the products minus the sum of the delta S0 of the reactants. So this is how it's going to look. So the products in this reaction are the CaO, which I have the value right here, and the CO2, which is here. So this is what I'm going to do. You got to remember to do the 1 mole. The coefficient is 1. In the balanced equation, the coefficient is 1. Okay, and then for the CaO, it's 40. And joules over Kelvin mole. So this here was the CaO. So moles are going to cancel out. Plus, now there's 2 products. So there's CO2, so then I'm going to do CO2. And CO2 is again 1 mole. And it's 214 joules over Kelvin mole. So again, what happens here is moles cancel out. Okay, minus, and then I have 1 product, or I'd say 1 reactant, which is CaCO3. So I've got again 1 mole, and it is 93 kilojoules. I keep saying kilojoules. Joules over Kelvin mole. Okay, not a bad idea to plug that in and calculate that out. So if you want to do that, I'll give you a second. I'll tell you what I get. I get 161. And the units would be joules over Kelvin. 161 joules over Kelvin. And like I said when I started, I said just by inspection, going back to what we talked about earlier, that this would be positive, and it's positive. So that kind of aligns with what I would have predicted. Did anybody try that, calculate that out? You got that, David? 161, good. Okay, not too bad, right? Not too bad. Okay, so here's what I want you guys to try. So here's the reaction. Again, you have to be given the entropies. So here are the entropies. Again, joules over Kelvin mole. So we got N2, 192, H2, and NH3. So this time, when the coefficient in this case, so for the H2, you would have had 3 moles. And for the NH3, you would have 2 moles. Okay, just take a minute. Go ahead and try that. Just see if you can calculate that out all the way to the final answer. And again, it says here, and it's something I should have talked about before we did this, but it says here, upon visual inspection, will this reaction increase or decrease entropy? What would you have predicted, a positive or negative entropy? Negative, good Lord. Because I got 2 gas molecules here, I have 4 here. I think this should be negative this time. So here's the NH3. What I get here is negative 199. Mason, you're exactly right. The units here are joules over Kelvin. Did anybody else get? And I said negative. We said negative, so that aligns with what I would have predicted. Did somebody say they got that? Samantha. Okay, good. Okay, so now, so how we calculate delta Yes, now I'm going to again skip a couple pages here. Okay, we already did that. I'm going to go through this because we kind of talked about this a little bit. This is going to lead into the main thing, and the third law of thermodynamics. We're not going to talk about that either. Okay, here's the key thing. This is the Star Wars music, the trumpet blast. Here is the key equation in this chapter. And this is, of course, this good to know. Formula sheet on the back, thermodynamics and electrochemistry, right down there. Delta G is called Gibbs free energy. Okay, and we're going to look at this, and I'll give you guys a second. This is a key page, probably of the whole chapter. This is the key thing. Everything culminates with this. The delta G is equal to delta H minus T times delta S. And if you remember where we started today, I said, okay, here was, here's what, okay, spontaneous, non-spontaneous, thermodynamically favorable, non-thermodynamically favorable. It depends on delta G. And delta G, when it's less than zero, when it's negative, it's spontaneous. It produces free energy. And this, I'm going to talk about this, and hopefully today, and if not on Monday, but when delta G is zero, it's at equilibrium. And you might want to write yourself a note here too, if you're taking notes. And I'll talk about this again either later today or on Monday. But this is when delta G is zero is when a phase change occurs. When a phase change occurs. So when we're going solid to liquid, liquid to gas, and that's important because if we know delta G is zero, then we can make H is equal to T times delta S. And we can do that again. If we come to that today or Monday, we'll talk about it. And then delta G is positive. The reaction is spontaneous in the reverse direction, which means it's non-spontaneous. So delta G is called Gibbs free energy. So this is a measure of whether or not the process will proceed without the input of outside energy. So this predicts, will this be thermodynamically or favorable or not favorable? And the first thing we're going to do is we're just going to look at the sign. Okay, I'm going to get to that here in a second. So again, this is trumpet blast, Star Wars music. This is the key thing in this chapter, is delta G. This, again, we're going to do here calculations with this morning, but I want to get into just looking at the signs. Okay, so I'm going to, again, some pages here. I'm going to skip through. I'm going to skip through this page, skip through this page. And I want to come back and do this page, but I want to go on to this page first. I'm going to come back to this. Okay, this is second key thing, is the signs. And here, and again, you can go back to the equation, the Gibbs free energy equation. You remember what we're trying to do to get this spontaneous. We want this to be negative. We want the delta G to be negative. And to be honest with you, the questions that they put on the AP test are usually the first two. So let's kind of just think about this process and go through this process here a little bit. Okay, to kind of give you an example of how this works. Usually, the third and the fourth one, they usually on the AP test they don't put that there because remember I said so. Well, let's look at every scenario. So if I look at scenario one, so if this is positive, delta H is positive, and this is positive as well. And if I want this to be negative, if the target is to get delta G to be negative, what has to happen to temperature? Positive, positive. Then you need to have a high temperature. You know how I always remember this is if I got a positive and a positive, then I need a high temperature. If I do a positive and a positive, I'm going to get a higher number. But we would need the temperature here to be a higher number for that to be negative. So if you think about it, it makes sense. But I can't think nearly as good as you guys can. So I always remember a positive and a positive. If I add a positive and a positive, I get a high number. Well, how about scenario two? So again, if I want this to be negative, so if I have a negative and a negative, so a negative minus a negative becomes positive, right? Right? Well, here then, I would need this to be a low number. So when I do my negative minus a negative, it's going to be a lower number, so this would be negative. So how do I remember this? You guys are, again, way smarter than me. You guys can remember the logic of this whole thing. But if I do a negative and a negative, that's got to be a low number. And again, this is the first two scenarios are what's going to be on the AP test, okay? If you look at scenario three, it's what I talked about. With the system, when the delta H is positive and delta S is negative, that can never, because you got a positive minus a minus, that becomes positive. This will never be negative. It'll never be spontaneous. That will never happen. So an endothermic reaction with a negative delta S. And then number four is if I have negative. Remember I said usually when reactions are exothermic, it's usually spontaneous, but not always. And usually when the entropy increases, it's usually spontaneous. So if I have a negative minus a positive, it is always going to be spontaneous. So here's the situation. Okay, so let's look at this. So we have H2O, solid, ice. We've had way too much ice lately, Juliana, around here. Supposed to be in the mid, supposed to be like 61 or 62, and every day it's like 33 around here. But this reaction, the delta H, is delta H positive or negative here? Is this an endo or exothermic reaction? Do you have to put energy in ice to melt it, or does energy come off when you melt ice? Is this endo or exo? This is endothermic, right? You have to put energy in ice to get it to melt, right? Right? What's the case with delta S? What happens with delta S in this reaction? Is it positive or negative? A liquid and a solid. It's positive, okay? So when is this reaction spontaneous? At high temperatures, right? Well, when does ice melt? When you take it out of the freezer, right? That's when ice melts. And when is it not, when does it stay as ice? When it doesn't occur is when it's at low temperatures. Okay? Again, that is kind of a big deal in this chapter. Okay, now let's go back here. So let me kind of go back. Here, we're going to do a couple calculations here, and I'm almost to the point. I'd like to do this slide and almost get done for today. But this slide's going to take us a little bit of time. I don't want to go too much too fast. Okay, so first of all, you see these delta S sub 0. That's what this means is standard state. It's a little bit like in first year chem. Today, my students have a test on gases, my chemistry students, and you know STP. Okay, and STP is 1 ATM and 273 Kelvin, 22.4 liters per mole. It's just different conditions. So standard state is kind of when, kind of room conditions under normal, okay, where we, because of our altitude, we would really never be at standard state. So when you see these uppercase little zeros, that's what it means. Standard state is pressure is 1 ATM, which we're not at 1 ATM. We're like 0.8 something, okay? I think, let me even see that. We might even be less than that, just to be accurate. Yeah, about that, 0.8 or something. So here in Colorado, because we're at a higher altitude, we would never really be there. Temperature 298 Kelvin, and they always call room temperature in Celsius is 25. Actually, 25 is kind of a warmer room temperature. Pure liquids or a 1 molar solution. So that's when you see the uppercase, when you see that. Okay, so we're going to calculate delta G for this reaction under standard state conditions. And so what I'm going to do here is I am going to give you, or I'm going to do this now. Again, I'm going quicker than I ought to, but again, I just want to get through, so because this is stuff, like I said, I really think we can do good on this. You guys can do good on this, on the AP test. And so I feel the same way about some of the things we're going to do in chapter 17, but you have to be given a table to do this. So here is, so here's the reaction. Okay, so I'm going to give you, or I'm going to write it on the board for myself. But here, so here is the delta H, 0 kilojoules per mole. Here is the delta S0 in joules over Kelvin mole. Here's the delta G0, and it is in kilojoules per mole. And there's two ways to do this. And so we've got NO2, and I got N2O4. So you have to be given these. Okay, so we've been asked here to solve for delta G, and I'm going to do it two ways. And so the next question I've got, is this reaction driven more by enthalpy or entropy? So I'm going to do both. So I'm going to solve for delta H. So my reaction here is 2 NO2 and N2O4. Okay, so I'm going to do what I was just doing. So on the formula sheet, I'm going to find delta H by doing the sum of the delta H of the products minus the sum of the delta H of the reactants. And again, that's why we need these table values. Okay, so the products are N2O4. So I've got 1 mole times 10 kilojoules per mole. So I have one product, and then reactants, so I have 2 moles, those are the 2, times 34 kilojoules per mole. If I look at this again, moles cancel out. And so if I do this in kilojoules, I think I get negative 58 kilojoules. Or really, it's probably 58.040. I just went to 2 sig figs. Anybody try that? And I'm going, oh, no, I'm going. Is that what you got? Okay, now let's do delta S. It's going to be the same thing. So it's going to be the sum of the delta S of the products minus the sum of the delta S of the reactants. So again, I need the table values. So I've got the N2O4, so I've got 1 mole. (304). The units are important here. Okay, and then I have 2 moles. Okay, what I get here then is negative 176 joules per Kelvin. Now, the whole point of the problem is to calculate delta G. Well, delta G is equal to H minus T times delta S. Well, now I've got delta H and I've got delta S, so I can plug everything in, but there's one problem I got before I plug in. And what's that problem? Well, I know because, and that's a great point, Mason, but with this uppercase 0, that's telling me this is standard state. So the temperature then is 298. So I do know that. But there's something else I'm looking at here that's not aligned right. It's the units. Good. This is kilojoules, and this is joules. And it doesn't matter which way I go. I just have to get the units to agree. And what I mean by I can either make this be kilojoules or this be joules. The way I did it is I made this be joules. So I had negative 58,000 joules. So now I'm just going to plug everything in. So I have negative 58,000 joules. That's delta H. Minus T, and Mason, that's a very good point. The temperature is part of this. And then what I've got for delta S is negative 176 joules over Kelvin. And again, now you can see what happens with the units because now Kelvin cancels out and everything aligns. And what I get when I do this, it'd be great if somebody could confirm this. I get this. Negative 5,552. Kara, did you try that? We good? Is that what we got? Okay, and then the question is, and doing it this way is more painful, but there's also, we can then ask a question, we can answer a question like this. Is this reaction driven more by enthalpy or entropy? So coming up with this number, that it's negative 5,552, was that more from the delta H or more from the delta S? The delta H, right, David? It's 58,000 versus 176. So this reaction was driven by delta H because of its value. But here's another way to do this. And we're going to do this one, and then we'll do one more the easy way, which is if I'm given delta G, which I am, I can do this. I can just do the same thing. The sum of the delta G of the products minus the sum of the delta H or delta G of the reactants, which if you look on your formula sheet, there it is right there. And so I could do it this way. And so let's do it. So I've got delta G, so I've got N2O4, so I've got 1 mole times 98 kilojoules per mole. So 1 mole, 98, minus, and then I have 2 moles, 52 kilojoules per mole. So if I do it this way, and again, it would be worth you seeing what you guys got. Negative 6. Which is a little bit different, but it turns if I really rounded that, because this is kilojoules, this is joules, so I went to the 1 sig fig. It really is aligning, okay? But the thing about doing it this way that's not as informative is when you do it this way, we can't answer the question of what is driving the reaction more. Is it delta H or delta S? Okay. Okay, last one we're going to do, and then we're going to stop. Okay, so here is this one, but this one we're just going to do it the easy way. So I'm going to have you guys do this. Here is the values. Okay, so I'm just going to give you the delta G values. Or tell you what, I'm going to give you both, and if for the sake of time, we're just going to do we're going to do it this way. But I'm again going to give you delta H, delta S, delta G. So if you care to try, you can. So CH4 is negative 75, 186, negative 51. O2 is 0, 205 is 0. CO2 gas is negative 393.5, 214, negative 394, and H2O liquid is negative 286, 70, and negative 237. Okay, what I want you to do is what it says right there is to solve for delta G, and just for the sake of time, and having to listen to me for a brutal hour, just do it this way. Just do it this way. The only thing about doing it this way is it's not going to be as informative. Just let's go ahead and take a minute and do that on your calculator. I'll get out of the way here. Should just be kilojoules and those cancel out. I got negative 817. We good? And I'll tell you too, if you care to look at this, the delta H, if you went through the process here, is negative 890.3 kilojoules. And the delta S I got was negative 242 joules over Kelvin. If you care to try that. So, okay. You guys have done good. Let's go ahead and call it a day. We still have a little bit more to go on 16. So kind of what's going to happen next week is on Monday, we're going to finish 16, and we're going to I'll tell jokes, and boom, we're going to get to work. We'll talk real quick, wrap up about the T-shirt, and we're going to get done with 16, hopefully get into 17, and then Tuesday and Thursday, we're going to get through 16 and get as much done as we can. So it's time to relax a little bit. Okay, Kyle, I'm done with you, buddy. So if you want to check out, you can. If you want to hang in there, you can too.
Great, thank you.
See you, Kyle.